We're now going to go kind of back to the future and talk about some aspects of Java threads. And you'll see why, as we get past the first part of the lesson, why we're covering this. The main reason we're covering this is if you take a look at your latest assignment, there's a whole bunch of places where you're checking to see if things are interrupted and throwing interrupted exceptions or cancellation exceptions or something. And so I really haven't explained thread interrupts in any great detail. In order to be able to understand thread interruption, you have to understand a bit more about the Java thread lifecycle. So we're going to talk about that starting here, and then we'll transition into how you start and stop threads, especially stop them. So we'll be focusing first on the states in the Java thread lifecycle. A Java thread, if you haven't figured it out by now, is a fairly complicated entity that has to interact with a bunch of other things in the operating system. And therefore, there's a life cycle that has to be managed carefully. In order to figure out how to manage the life cycle, it helps to understand what life cycles threads go through in the first place. So we're going to talk about the transitions that occur. It's basically a state machine. And we'll focus primarily on starting and stopping threads. But first, we'll talk about what the life cycle is. You actually don't have to understand all of the details of the thread internals and the thread states and so on in order to program with threads. But it'll help you be a better programmer. It'll help you understand some maybe weird messages you'll get at different points by understanding what's going on under the hood. OK, so let's first start by talking about the thread state machine. You can take a look at this link to find out more about thread state. And you can also take a look at this link to see another UML-like diagram that illustrates the states of a thread. I drew my own because I wanted to be able to walk through it sort of state by state and animate how the states change. So when you first create a thread, when you say new thread or new my thread or whatever you do to create a new thread, that's going to create the thread in the new state. So you make a new thread, you're in the new state. Can't do much with it at that point, it just exists. Things get interesting when you call start on a thread. When you call start, that will launch the thread, and we'll talk more about what it means to launch a thread in just a second. But in essence, once the thread is launched, in other words, once the runtime stack is created and it's entered into a thread control block by the operating system, kernel, et cetera, et cetera, et cetera, then the thread transitions into the so-called runnable state. Now keep in mind, this is the Java thread, which is a little wrapper around the underlying operating system thread to give you an object-oriented abstraction to accessing what is otherwise a low-level kernel artifact. So now you're in the runnable state. Runnable doesn't mean you're running, it just means you're capable of running. How you start to run is by having the scheduler pick your thread, and then it'll go ahead and let that thread start to actually run on a core. And of course, it's the thread scheduler at the operating system that controls how all this works, because there could be lots of threads that are waiting to run. So finally, your thread gets to run, and then it transitions into the running state. And of course, when it's in the running state, then it's going to run. And literally, it'll cause the run hook method that's defined on your runnable or your thread object or whatever you use to provide a way to run the thread. It'll give it that callback, and that's where you put your code. So your code is in run. Now, once your code is running, it's got a bunch of things it might decide to do. And those things will end up potentially changing the state of the thread. So one thing it might do is the thread might decide to put itself to sleep. Or it might decide to wait. If you recall the monitor object wait operation we talked about, it might decide to join on another thread with a timeout. So anytime there's a timeout related operation, that will transition the thread into the timed wait or timed waiting state. At that point, it's no longer running. It's waiting for either the resource to happen or the timeout to elapse, one of the two. When the timeout elapses or the operation completes, whichever comes first, that will then cause the thread to become runnable again. But it doesn't mean it starts up right away. It just means that it's capable of being selected by the scheduler when its time has come, and then the scheduler will go ahead and run it once again. So now it'll be running. And once again, the run hook method will get called back. So the run hook method gets called back. It does some other stuff. What are some other things it can do that affect state, you may ask? Well, one thing it might decide to do is it might decide to try to access a guarded resource. And so it may try to go to somebody else's monitor object and make a method call that causes it to go into a synchronized method. And if that call to the synchronized method is already being used by another thread, then that's going to cause this thread to block or go into the blocked state. And the blocked state simply means it tried to get the resource, but it couldn't because it wasn't currently available. So obviously when it's in the blocked state, it's not running either. So it could be blocked waiting to get the intrinsic monitor lock. At some point, it'll be its turn. The resource is acquired because a different thread released it. Once again, we transition into the runnable state. Don't start to run. At some point later, the scheduler will pick us to get a chance to run. And then we're going to go run again. Now, ironically, the thread state for blocking I/O is runnable. And you can read this link, which is a little hard to see here, but you can see it in the slides when I put it out later, in order to understand the subtlety of this. It's kind of bizarre. When it's your turn, the scheduler will give you a chance to run. You'll get a chance to have the run hook method called back. Now and actually it's not so much the run hook method's called back, it's that wherever you were left off in the run hook method keeps going because you were suspended. And at this point you might decide to do a wait. In this case it's a non-timed wait. So in this case we're going to have a wait operation calls. That puts us in the waiting state. We're off to the side in a wait queue. Remember, each monitor object has one and only one wait queue. When somebody else notifies us, or someone notifies all, and that happens to include us as well, then we wake up and we become runnable again. Then the scheduler once again will transition to the running state and will keep running in the run hook method. Finally, the run hook method is going to exit either because it fell off the end or there was an exception thrown that was not caught by the run method or anything that it called. So at that point, we transition to the terminated state and the thread is finally done, at which point the system can reclaim its resources when no one else can access it. Okay, so that's basically the set of states that the thread can go through in Java. And once it's all finished, the states can be, the resources can be reclaimed. The obvious thing to notice here, by the way, if you take a look at all these states, is there's a lot of stuff going on. And so starting a thread and having it run and blocking and waiting and timed waiting and so on and so forth, all of those things have a fair amount of time involved to have the operating system make them work the way they're supposed to work. So that's why you should be thoughtful when you try to use a thread, because if you just spawn them willy-nilly and have them run to do very short-lived things, it's probably going to be slower than just doing it in a single thread. So I'll show you another view of that in a second. But the key thing to remember from this discussion is that threads are not super inexpensive. They cost you something. So now that we've talked a bit about the thread lifecycle stages, let's spend some time talking about the detailed steps involved in starting a Java thread. And then that way we'll cover stopping Java threads on Monday. So starting a Java thread has a bunch of different things going on. It's actually quite complicated to do this. It takes a fair amount of time in the collaboration between the Java virtual machine and the operating system. And thread startup time is non-trivial, even on fast processors, although it's obviously getting better as hardware gets faster. So when you call start, that triggers ultimately the execution of the run hook method. And as I said before, it doesn't happen immediately, but it goes through a sequence of steps that ends up causing run to get called back. Many steps occur at various layers of the class libraries, the Java execution environment like the virtual machine or the Dalvik or Art runtime on Android, and in the operating system. Different versions of Java, different versions of Android running Java will implement these layers somewhat differently, although they all do more or less the same sorts of things. You can take a look at the source code if you want for access to the Android and Java source code. There's lots of good stuff there to take a look at if you want. So it's important to realize that a lot of resources are consumed starting threads. So use them judiciously. Don't spawn 2 threads to add 1 plus 2. That's way overkill. You typically want to spawn threads if the things you're going to do in the thread are going to take a lot longer than the time required to start a thread. A good example would be anything that's going to block or things that you want to have running on multiple cores. So when you call myThreadStart, which occurs at the application layer in your code, that on some versions of Android will call the start method of the Java thread, which is in the execution environment, such as Dalvik or Art. And then under the hood, that will call vmthread.create, which is a native method. It means it's a method that's implemented in C, but it's part of the virtual machine of Android. That then calls into this JNI method. This is, again, the Dalvik implementation. It may be somewhat different in Art, but it's the same idea. So it calls this Dalvik Java Lang VM thread create method. That ends up calling VM, which stands for Dalvik Virtual Machine, create interp thread. That finally ends up calling pthread create. Pthread create is a method that comes from the pthread library. So now we're in sort of GNU Linux land. And this is essentially the transition point between the happy world of Java and object orientation with abstraction and type checking and so on, into the cold, gray, sort of dreary world of C, which is where the operating system works. At that point, the Android Linux kernel will create a thread, which has a runtime stack plus other stuff. That's a whole other path. That's probably actually where 99% of the time is spent. We are not going to go through that code, but if you're really, really feeling masochistic, you could always read all the code here. This is the Android source code to see what it does under the hood. At some point along the way, the code will call back to something in the execution environment of Android, such as interp thread start, which is an adapter. And that will call DVM for Dalvik Virtual Machine call method, passing in the object and the context for it to run. That will finally end up calling back the run hook method on the thread that you originally started. Right? So look at all those different steps. And this is not all of them. I'm just giving you an abbreviated list of steps. So many, many steps involved here. So the key point of all this is lots of steps, lots of overhead. Don't do this unless you really need to have a thread.